Hello everyone. In this video I'm going to talk about breadth first search algorithm or BFS. Why is breadth first search? Well, it's an algorithm that explores the search tree level by level. Because of this layer by layer approach, this algorithm is guaranteed to find the shortest path in the solution, provided that all edges or steps in the path have the same cost. Let's see how this algorithm is implemented. To implement this algorithm, you must use a specific data structure called a queue. A queue operates on a first-in, first-out principle, sometimes referred to as FIFO. The first-in, first-out principle basically states that the first element that gets appended to the array must be the first element that gets out of the array. Let's explore how this works using a sample tree. On start, we take the first node, which is the root node labeled as 10. The first thing we do is enqueue that node to our empty queue. Next, we dequeue the first element in the queue, which happens to be the node 10. When we dequeue a node, we expand it, meaning we find all the neighboring nodes to that node. The neighbors of 10 are 5 and 15. We then enqueue those neighbors, 5 and 15. We then go back to the queue and dequeue the next element, which is 5. We then expand 5, which gives us 3 and 7. We enqueue those 3 and 7. Now the next element in the queue is 15. We dequeue it. Then we expand 15, which gives us 12 and 80. We enqueue those 12 and 80. Now our queue contains 3, 7, 12, and 80. Notice how we've processed level 1, which is 10, and level 2, which is 5 and 15, before even touching the nodes on level 3. Now we head on to exploring level 3. To continue this process, we dequeue 3. Trying to expand it, we find no new children nodes. Then dequeue 7, expand it, and so on. Each time we dequeue a node, we process it and enqueue its unvisited children. By the time the queue is empty, we have covered the whole search tree level by level, in the correct BFS order. Now, let's have a look on the code structure. This is pretty much how the algorithm is implemented. The BFS function takes the starting node and the graph. Since BFS is an iterative process, it does not use recursion like DFS. Instead, it relies on a loop driven by the queue. First, the algorithm initializes a queue and a set of visited nodes. The starting root node is marked as a visited node and then enqueued. The algorithm enters a while loop that runs as long as the queue is not empty. Inside the loop, the algorithm dequeues the first element and calls it the current node. It then loops through all of the current node's neighbors. If a neighbor has not been visited, the algorithm marks it as a visited node, and then enqueues it. Now, let's talk about performance metrics. Let's discuss the performance of the BFS algorithm. First one is completeness. Is this algorithm considered a complete algorithm? The answer is yes, because the algorithm explores the tree level by level. It is guaranteed to find a solution if one exists. Even in infinite trees, as long as the solution is at a finite depth, the level by level approach prevents it from getting stuck on an infinitely long path. Second metric is cost optimality. Is BFS cost optimal? The answer is yes, but as long as all step costs are equal. BFS guarantees that the first time it's going to find a solution, that solution will have the minimum number of steps, since it systematically checks for all the paths of length d before checking any path of length d plus 1. Next metric is time complexity. The time complexity is proportional to the total number of nodes the algorithm has to explore in the worst case. For a tree with a branching factor of b and a solution at depth d, the time complexity is b to the power of d. In the worst case, the algorithm has to examine every node up to the depth where the solution exists. Lastly is space complexity. BFS is known to have a very large space complexity. Since the algorithm must keep track of all nodes on the current level in the queue before it can proceed to the next level, the memory required grows exponentially with the depth. For a solution at depth d, the algorithm must store all nodes up to that depth. The space complexity in that case is b raised to the power of d. As you go deeper into the search tree, the number of nodes at the level grows exponentially. For example, if a tree has a branching factor of 10 and the solution is at depth 14, you would have 10 to the power of 14 nodes at that level. This is an enormous number of nodes which would indeed exceed any memory capacity of any standard computer. This is the biggest drawbacks of BFS.